In connecting up instrument transformers to relays, it's obvious that we have to pay particular attention to the direction of current flow, that is, polarity. In discussing polarity in an AC circuit, we are referring to instantaneous values of voltage and current. But what is meant by polarity? As an example, look at this typical transformer. Here, the primary and secondary windings are wound on separate legs of the core. They can be wound in either the same or opposing directions. Note that here, both primary and secondary windings are in the same direction. If the windings are wound in the same direction, the secondary current flows in the same direction as the primary. The polarity of the transformer is termed additive. We can see that current flows out of the secondary winding at the opposite end to current entering the primary. To help identify this, the terminals are marked like this. By convention, H refers to the primary and X the secondary. H1 is current into the primary and X1 is current out of the secondary. Conversely, when primary and secondary turns are wound in the opposite direction, the secondary current flows in the opposite direction to the primary current. The transformer is said to have subtractive polarity. Here, the secondary current flows out at the same end as the primary is entering, and the terminals are marked accordingly. In instrument transformers, the windings are almost always opposing, that is, subtractive. On schematic diagrams, the CT is often shown like this. The plus sign indicates where the primary current flows in and where the secondary current flows out. You will also see CT polarity markings shown as X's, dots, or even squares. This identification enables us to connect the secondary windings to the relays in the correct relationship. The same polarity rules apply for potential coils. The voltage transformer is marked on both the primary and the secondary. Before connecting a relay to a CT, it is advisable to check that the polarity markings are correct. One of the most common methods used to determine polarity is the kickback method. In this method, a DC moving coil voltmeter is connected across the CT primary winding, that is, the high voltage side, with the positive lead connected to the terminal marked H1 and the negative lead connected to H2. The positive terminal of a dry cell battery, typically a 1.5 or 9 volt, is then connected to the secondary terminal marked X1. The negative terminal of the battery is connected to X2 with an open switch in the line. Beware, the current applied in this test must be limited to a very low value. That is why a high-resistance dry cell is recommended to prevent the core from becoming magnetized. Now, close the switch. When it makes, you should see an upscale kick of the meter if the polarity markings are correct. Take care not to apply the voltage to the high-voltage terminals, primary in the case of a CT. Otherwise, an extremely high voltage will be induced into the secondary. Voltage transformers can be checked in the same manner, but another check can also be used by applying 120 volts AC on the primary. As this is a 10-to-1 step-down transformer, we should read 12 volts across the secondary terminals. Jumper a primary and a secondary terminal on one side of the transformer. Connect a voltmeter between the two terminals on the other side of the transformer. Because of the jumper, the voltmeter will feel the effects of both the source voltage and the induced voltage. In this VT, the windings are connected in a subtractive configuration, so the induced voltage is in phase with the source voltage. The voltmeter responds to the difference of the two in-phase voltages. Therefore, on our meter, if the terminal polarity is correct, we should read 120 minus 12 equals 108 volts. For an additive transformer, the induced voltage is out of phase with the source voltage, and therefore we should read 120 plus 12 equals 132 volts. You can see now where the terms additive and subtractive come from in referring to polarity. Of course, there are other ways of checking polarity, and some equipment that's available also checks ratios. Polarity is extremely important when it comes to connecting up three-phase transformers. Let's consider the case of a distribution transformer, say 4,160 volt primary to 416 volt secondary connected Y-Y. This could be a three-phase unit or three separate single-phase transformers, as shown here. On a single line diagram, this arrangement would probably be shown like this, with the Y-Y symbols indicating the connections. More detail will be shown on the circuit diagram. First, let's look at the primary. The polarities are clearly marked. Here, the positive terminal of each primary is connected to its respective 4,160 volt line, while the negative terminals are connected together to form a common neutral. The line to neutral voltage is 2,400 volts. This forms the Y connection, and the phase relationship for each primary will appear 120 degrees apart, like this. Now remember, there are three separate transformers, each of 10-to-1 ratio. The voltage induced in each secondary, 240 volts, will be in phase with its respective primary. In certain cases, they may be 180 degrees out of phase, but for simplicity, we will consider the secondary voltages in phase. Now look, we have three secondary voltages available, displaced at 120-degree phase angles. They could be connected to form a delta arrangement like this, or a Y connection like this. By following the polarity markings, we now have the correct phase relationships and line-to-line voltage, 416 volts. But suppose we had inadvertently connected, say, phase A the wrong way around. Now the A line would be seeing a negative voltage, and the phase relationship would look like this. Phase A is now 180 degrees out of phase. And look at the line voltages. Instead of 416 volts, we now have only 240 volts between lines A and B, and the same thing between A and C. Many relays operate by comparing phase relationship between voltage and current, or perhaps some other quantity. A typical example is the directional sensing relay that we discussed in the previous videotape. Here we see typical connections for a directional ground fault relay. This 33 kilovolt bus is being fed from the secondary of the transformer, which is Y connected and has a grounded neutral. The outgoing feeder is protected by this breaker, and the three line CTs are connected to the sensing coil of the directional relay. Note the polarity of the CTs is clearly marked on the schematic. In this particular scheme, the polarizing quantity is obtained from the main transformer neutral, so this is current polarization, not voltage. Again, the correct polarity for the neutral CT is marked on the schematic. The correct polarity is also marked on the relay. So let's see how this works. A ground fault on the line would cause a return current to flow up the neutral And consequently, current will flow through the relay polarizing coil in this direction. At the same time, the line CTs will sense the out of balance due to the ground fault, and current will flow through the relay sensing coil in the correct direction to allow the relay to trip. For a ground fault on the bus, the current flow would be in the reverse direction and so block tripping. You can see how important it is to get polarity right when making connections. If either of these relay connections is reversed, the relay would perform completely opposite to our needs. It would allow tripping for ground faults outside the zone and would block tripping for those within the feeder. Okay, so at this point, let's take a break, and then we'll come back and talk about phasor diagrams. For now, switch off the tape and thoroughly go through this material in your workbook. In the last segment, during our discussion on polarity, we looked at the voltage relationships between three interconnected single-phase transformers. You'll remember this circuit diagram, but in order to understand this, it was necessary to also study the diagrammatic representation of the phase relationships between the various voltages on both primary and secondary side. This diagram is known as a phasor diagram. It shows the magnitude and the phase relationship between the various voltages in the system. This is for a fixed moment, an instant in time. This situation is similar to the merry-go-round. When you stand on the sidelines, you see the red, white, and blue horses passing before your eyes. But if you stand on the merry-go-round, all the horses appear to be stationary. Now, let's go back to our phasors. We know that in practice, all of these values are constantly changing their position, rotating at the same speed as our system frequency. But it is important to note that the relationship between all of the values remains the same. And after all, this is what we are really interested in. So, for the purpose of study, it's convenient to hold the rotation and fix all of the values, just as though we are rotating with the phasors. For example, let's look at this simple representation of a single-phase voltage and its associated current. The length of this line is proportional to the voltage, and similarly, current is represented by this line here. Normally, the magnitude represents RMS value of voltage and current, the values indicated by most meters. Phasors were referred to as vectors in the past. But some years ago, the term phasor was adopted so as to distinguish this diagram from a vector diagram as used in space and surface navigation. I'm sure you'll continue to hear the term vector used, but phasor is the correct terminology. This angle between voltage and current represents the phase angle displacement. In this case, the current is lagging the voltage. We know this because this arrow shows us that the phasors are rotating in a counterclockwise direction. And from our position in space, we will see the voltage phasor before the current. You may occasionally see the arrow indicating clockwise rotation, but normally the arrow is not shown because the generally accepted standard is that phasors always rotate counterclockwise. Here, we're looking at voltage and current in one phase only. When we add the other two phases, the phasor diagram will look like this. We can see that it is a perfectly balanced system. There is 120 degrees displacement between the voltages of phases A, B, and C. Also, the magnitudes of voltages and currents are the same, and the phase angle between voltage and current is the same in each phase, so we have a balanced load. Bearing in mind the counterclockwise rotation, the phase sequence, or phase rotation as it's sometimes called, is A, B, C. From our position in space, we would see passing in front of our eyes phase A, then B, then C, and then A, and so on. However, some power systems work on a different sequence, ACB, and in this case, the phasor diagram would be relabeled like this. This delta Y transformer is feeding a three-phase, four-wire distribution line. A delta Y transformer has a 30-degree shift in voltages and currents between primary and secondary. In fact, as this example will show, the polarity markings and connections shown here have the primary leading the secondary. The neutral is grounded. First, phase relationships on the Y-connected low-voltage side. Plot the phasors for each phase voltage, that is, from line to neutral. Starting with line A, we plot VAN on the vertical reference. Note we could have used a horizontal reference. As this is a Y-connected secondary, we can now draw the other line to neutral voltages, VBN and VCN, each at 120-degree phase displacement. The phase sequence in this case is ABC. Also note, we are using lowercase letters to denote secondary phasors. But what about the line-to-line voltages? For example, line A to B. To get VAB, we go from line A to neutral, VAN, and from neutral to line B, VNB. VNB is the reverse of VBN. So now we must add VAN and VNB to get phasor VAB. We find that VAB is leading VAN by 30 degrees. Similarly, the voltage between lines B and C, that is VBC, is leading VBN by 30 degrees. And the same relationship goes for VCA. Let's now take a look at the relationship for current. Considering the load to be at unity power factor, we know that the line current IA is in phase with the line to neutral voltage VAN. So we can draw the IA phasor along phasor VAN. Similarly, IB is in phase with VBN, and IC is in phase with VCN. Of course, if the power factor is, say, 0.95 lagging, then all of the currents will be offset by 18 degrees. So much for the secondary. But let's move over now and draw the phasor diagram for the primary of this transformer. Usually, the primary and secondary phasors are drawn on the same diagram, but in this case, for clarity, we'll construct a separate phasor diagram. Note that the primary is connected in delta. Phase A is connected between line A and C, phase B between line B and A, and phase C between line C and B. Now remember, for each phase winding of this transformer, the voltage on the primary and secondary sides must be in phase as they are wound together on the same leg of the core. So when we draw the first voltage phasor for phase A, the voltage vector, that is VAC, must be along the same line as VAN in the secondary side phasor diagram. We're using capitals here to define the primary side of the transformer. The primary voltage on phase B, that is VBA, will accordingly lie along the same line as VBN, and similarly with VCB. Sometimes confusion can arise because the phasor diagram looks like a Y arrangement, but we know that this primary is connected in delta. An important point to remember is this phasor diagram is not meant to show electrical connections, only phase and magnitude relationships. We know that delta connection phasors can be shown like this. But if you look at the direction of voltage, here A to C, here B to A, and here C to B, you can observe that they are the same. So either phasor diagram can be used to represent delta or Y circuit connections. Now let's look at the currents in the primary with a unity power factor load. Clearly in phase A, IAC primary is in phase with IA secondary. Similarly, IBA primary is in phase with IB secondary. And likewise, ICB is in phase with IC. Therefore, IAC is drawn on the phasor diagram in phase with IA, and IBA is drawn in phase with IB. Similarly, ICB is drawn in phase with IC. But what is the current in line A, that is IA? Well, look, clearly the line current IA is the sum of the phase currents IAC and IAB, which is the reverse of IBA. Therefore, plot IAB on the phasor diagram and add IAC, which gives IA. We find by inspection that the line current IA will be 30 degrees ahead of its respective phase voltage VAC. Similarly with line currents IB and IC. IB equals IBA minus ICB, and IC equals ICB minus IAC. So there is a 30-degree phase shift of currents as well as voltage in a delta Y transformer, as you would expect. The line current IA in the Y-connected secondary is 30 degrees lagging the line current IA in the delta-connected primary side. Comparing the phasor diagrams, we can study the relationship between primary and secondary voltages. First, for clarity, remove all primary currents. Then superimpose the secondary line-to-line voltages on the primary voltages. Then reverse CA to AC, AB to BA, and so on. Look, now VAC secondary is lagging VAC primary by 30 degrees. And the same thing goes for the other line-to-line voltages. This is an important conclusion. This delta Y connection produces a phase shift of 30 degrees. Moving from high voltage delta to low voltage Y provides a 30-degree lag, and vice versa. This is, in fact, in accordance with the NCIEEE standard, which states that for Y delta or delta Y transformers, the high voltage side should lead the corresponding low voltage side by 30 degrees. Now, if the transformer is Y delta, then different connections must be made to achieve the 30-degree lag on the low voltage side. Here we see the arrangement and the corresponding voltage phasors. You can see that the secondary phase voltage VAB is wound on the same leg as the primary VAN. So they can be drawn on the same phasor. But look, the primary line-to-line voltage VAB is 30 degrees in advance of secondary line-to-line VAB. Similarly with VBC and VCA. So the ANSI rule has been observed. The high side voltages lead the low side by 30 degrees.